Good afternoon, everyone. Thank you so much for joining us. My name is Katie Rowley. I'm with the NOAA Central Library, and we are very happy to host today's NOAA Innovators Talk. A few logistical pieces first. If you can't hear the audio, or if you are having trouble with the visual components of this seminar, please try logging off of GoToWebinar and logging back in. That solves most issues. If that doesn't solve your issue, you can always email us at library.seminars@noaa.gov, and we can try and troubleshoot that with you. If all else fails, we are recording this seminar, and it will be hosted on the library's YouTube channel after the fact. We are accepting questions today, but all the questions are going to be answered at the end of the presentation. So you will note that everyone is muted. Please put your questions into the question panel. And with that, I'm going to turn it over to Tiffany House to introduce our speaker.
Thank you, Katie. Good afternoon, everyone, and good morning to some. My name is Tiffany House, and I am the NOAA SBIR Commercialization Specialist. The SBIR program provides small businesses with equity-free funding to conduct research and development work that will potentially lead to the commercialization of innovative products and services. TruNav received a NOAA SBIR award in 2015 for his Phase 2 research. This technology, which will be highlighted today, is available for a Phase 3, which means it can be acquired through a relatively easy process as a sole source procurement for NOAA or other federal agencies. AccuTrace is a differential global navigation satellite system capable of providing high precision positioning accuracy for quasi-static scientific mapping and survey applications. AccuTrace utilizes coarse data in addition to advanced error modeling, fault detection algorithms, and innovative filtering methods. Samer Khanafseh is the co-founder and principal of TruNav LLC and a research assistant professor at the Illinois Institute of Technology. His expertise is in high accuracy and high integrity navigation algorithms for close proximity applications, cycle ambiguity resolution, fault monitoring, and robust estimation techniques. He is an associate editor of IEEE Transactions on Aerospace and Electronic Systems and was the recipient of the 2011 Institute of Navigation Early Achievement Award. So, without further ado, please give your full attention to Samer Khanafseh.
All right, thank you, Tiffany, and thank you, Katie, for organizing this presentation. And I would like to thank all the audience for dialing in to this. So today I will present AccuTrace, a sub-centimeter vertical level positioning system that was funded by NOAA. Okay, slide 2. So AccuTrace was developed as a Small Business Innovation Research, or SBIR, award by NOAA. Specifically, it was by NOAA co-ops. And we passed through Phase 1 and Phase 2, as Tiffany just mentioned. And the goal was to develop, implement, and experimentally validate a cost-effective new differential global navigation system, or DGNSS, capable of providing a sub-centimeter positioning accuracy for quasi-static scientific mapping and survey applications. And hopefully, I think in the following slides, I'll go through and dissect these in more details, and we'll discuss about the project. The motivation for this from NOAA's perspective is to be used in its National Water Level Observation Network. So this network of devices monitors the levels in all water surfaces in the U.S. And what we're building here is not necessarily to measure the water level, but to monitor the stability of the device that measures the water level. Okay, so you can imagine that these are just two copies or two pictures of some of these platforms that I found online. And you can imagine that those devices would reside on these platforms. and they kind of shoot a radar down the water surface, and from that they measure how far that water is from the device. However, due to different conditions, the platform itself could be slowly moving, and what NOAA needed is a device that will detect this motion or measure how much is it changing. So that's why the term of vertical stability. The goal was to monitor how much this motion vertical is, and the accuracy needs to be like sub-centimeter, as I mentioned. Other applications that could use similar technology include structure monitoring, scientific applications, remote sensing, and single antenna surveying. So if you think of high precision GPS navigation or GNSS navigation, the first thing that comes to your mind if you're close to the field or use devices like that or survey devices is RTK, or real-time kinematic. However, usually those are not they're not cheap. They're pretty expensive, and they have some limitations as well. So the goal here was to provide a subscription-free alternative, meaning that the whole solution is inside this box, whatever that box will be. Okay, and also not to rely on the RTK service itself. So in order to do so, AccuTrace submitted the phase 1 proposal, and we showed the feasibility of building such a system. And in phase 2, we built this prototype with the pictures that you could see there, with input interfaces that meet NOAA's requirements. So AccuTrace uses advanced filtering algorithms to provide reliable sub-centimeter accuracy that meets the requirements. So how did it work? Instead of using the RTK network itself, TruNav decided to go to the NOAA's existing continuously operating or operational reference station or course stations. So this is a network of antennas and GNSS receivers distributed over the U.S. As you see in the map on the right-hand side, and it's free, public. So you could access the data from this, all these antennas and devices, and therefore external augmentation will not be needed. The challenge compared to RTK is that we don't need this very dense network as RTK needed. We could work with a relatively sparse network as the core station. Like the distance between these even in the ones that look like really dense in this map, for example, if you look at Michigan, the distance between these stations are in like between 40 to 100 kilometers. So in miles, that's about 20 to 60 miles. So with RTK, usually that's a little bit challenging, especially to achieve the sub-centimeter accuracy. But I think that's part of what we worked on in this proposal in this project. And the disadvantage compared to RTK, just to be upfront here, is that there's no real-time positioning. So we cannot provide real-time, and the limitation here is the course data availability itself, is that NOAA doesn't provide the course data publicly in real time. And I think I would like to use this podium here is just to call for anyone who's involved in core stations to know how much valuable the data itself when it's not online. And if it goes online, I mean, there are so many things that we could do with it. And if you're interested, just contact me. We can talk about many applications, including not only positioning, it could be even reach up to national security. So the way also AccuTrace works is that it takes the data from these stations, it fuses it, the multi-constellation. For now, we're using GPS, Global Positioning System, the US system, and GLONASS. the Russian. As Galileo becomes available, it's something we're keeping in mind is to keep improving on AccuTrace and add Galileo as well, the European navigation system. So it fuses these measurements in a simplest filtering algorithm and error modeling to improve the reliability and accuracy of the positioning system. So to give you just a flavor of one of these enhancements that we made, so we had a special error modeling techniques that we use in order to get the accuracy we're talking about. We had fault detection, meaning if there are erroneous measurements, or in some cases even not very good core stations. We could also autonomously, the software would detect that and decide not to use those core stations anymore. And in addition to filtering methods and even optimized station selection logic, reference stations. And this is an example on the right-hand side in this figure of the performance before and after using one of the examples here, which is I'm talking about the fault detection piece or component of this project. So there's a blue line shows the accuracy of post-processing some data. This is the error on the y-axis versus time in hours. And you could see that we definitely had erroneous measurements there. And if I recall, it was even a combination in this case. It was the station itself wasn't one of the best. And even we had some issues with certain satellites for certain signals could be related to excessive multipath. So the software, once we enable this detection, what it does is it knows that some of this data is not good and it doesn't use it. And if it's coming from the same station, it throws the station out and replaces it with another one. And that's what provides now the black trace that you can see there, which clearly is hovering around 0 centimeter with an error that meets the 1 centimeter standard deviation. So this just shows you one of the components that we do in order to get such accuracy. In order to validate this, what we decided on doing during I recall maybe the first year of phase 2 is to run the AccuTrace software on all core stations, the ones that you saw on the map before, and use these stations as surrogates. So what we did is we go to the data from that station and we say, well, we'll assume that that station is the platform, kind of a surrogate to the platform, and we process the data for a few days. And we generate a plot, as you see there, this bottom piece. We generate the blue curve is going to be the error, the accuracy, and the red lines here represent the expected value of the standard deviation. So we're even doing better than what we're expecting, and even that is around 1 centimeter. And this is kind of a tool set that we provided at the time to NOAA co-ops just to double check out or look at the verification that we've done. So it shows you the station that we use as a surrogate, and it shows you all the 6 surrounding stations with these lines or these rays that we selected for finding the position of this single station. This is an example around Chicago area, but we've done this to all 1,700 station core stations. We didn't run every single core station because when we did that, also we found certain stations that have problems, certain stations that have issues or gaps, data gaps that we didn't run, and that's why the 1,700 is not the total number of core stations in the U.S. It's closer to around, I think, 2,000 or so. But these are the ones that we analyzed and we could plot the results for. When we did that, we plotted this on a map, and we color-coded those small triangles or pyramids. So anything in blue, you could see that this has a standard deviation of 1 centimeter or less. Once we go to the cyan, green, and yellow, then we're going from 2 to 4 centimeter accuracy. and red definitely were going 5 centimeters or more. One thing that you could observe here is, wherever we have good course coverage, course network coverage, we most of the time have blue results, meaning that the accuracy was meeting the 1 centimeter. And whenever there are large gaps, like in the plains, you can see that we're losing some precision there. And there's so many differences, so many reasons for that. And those who are familiar with how differential GPS work know that with longer distances, many of the error modeling would start breaking down because the error propagates with the distance between these antennas, or the user and the antenna. So it was expected, we were expecting to not get very good results, and I think our validation showed that as well. So in the second year of the phase 2, we started building or working on the hardware side of AccuTrace because it was one of the requirements to provide prototypes to co-ops so that they could take them and also test them on their facility. So we delivered 5 prototypes, and the prototypes have been tested in NOAA's co-ops facility. And the way we did that is I'm trying here to walk you through a whole experimental setup, so please bear with me. So what we have here is the mock-up of the platform, to kind of at the backing, back parking lot of the co-ops facility. We had 2 antennas on these 2 poles, just because we wanted to run 2 different, these were the early stages of the prototype, and we wanted to test different hardware components. And at the same time, what the co-ops guys decided to do is, we will install this, we will run the system, we would leave the facility, and the test will be over 5 or 6 days. During this period, at times we don't know, or we are not even available or around, what they will do is they will go and move one of these antennas up or down, just to mock a scenario where the platform has changed in altitude or height. Of course, they will measure how much they moved it, and they wanted, to validate, see, do we get the same result or not. And this is the result that we reported using AccuTrace. So notice here that this is the date, and each one of these blocks on the x-axis is about 6-hour period. 8-hour period. So each 3 blocks is 1 day. On the y-axis, it's the vertical position estimate with respect to some reference point. That we could ignore this for now. But each one tick or one block on the y-axis is 5 centimeters. So you could tell now with the first probably 1.5 days or 2 days, the solution was stable within 1 centimeter standard deviation. And then once the antenna was moved or started, in order to move this, they had to kind of unscrew some of these and start the motion. The antenna, the solution of the vertical position started changing, and it went up to 30 centimeters, and it stabled over there. And this exactly, it was 0.98 feet. And this matched what the distance that the antenna was moved by. So this is kind of was our final validation and verification of AccuTrace on field. So in summary, TruNav built and delivered 5 functional prototypes that meet NOAA's accuracy and trace requirements of AccuTrace. We demonstrated that AccuTrace can achieve sub-centimeter capability in US-wide tests using all core stations as surrogates and in real time in the NOAA's facilities. So the results were, as I mentioned, in general, sub-centimeter, with the exception of few locations where the surrounding course coverage was not very good or was not sufficient. And this is where I would like to, I would like to commend those who are working on course from NOAA. The idea is, I can't even say enough about it, for all different purposes and scientific purposes, and even in this project. And I hope that those could even spread more. And as I mentioned, one thing that I would like to see is at some point to have real-time broadcast of the data. AccuTrace can be provided as hardware or software. Since the hardware in this case is all off-the-shelf component. I mean, it was, if I want to be precise, it was a GPS antenna, a GPS receiver, and we have a computational unit that was running on Linux. So you could use a laptop. We were using a small embedded system. I think we tested with Raspberry Pi and it was working fine, as long as you handle the cooling part properly, just because the computation is heavy and therefore it's going to heat up. So we realized that was one of the challenges, and we kind of handled that. And that's all. Then you just install the AccuTrace software and it takes it from there. Where we're going next with this is currently it's being licensed as a software package to NOAA's co-ops. They wanted to, instead of the hardware, they wanted also now to see if they can use this for other things and also to run extra tests beyond the 2-year the 2-year phase 2. And at the same time, they wanted also to have the option of asking for features and changes and modifications. So we signed a contract last December, if I recall. And so we're still working with them on additional features and testing. One of the features they were interested in, as an example, is not to be bound by core stations. Say, for example, they have access to other reference data like NGA or IGS. So we did provide that as a feature as well, with a user input where to get the data from and the format. Or to post-process data locally on any computer or even on a server, if that's an option that they wanted. One thing that we, internally from the TruNav side of things, one thing that we're working on is, or we're hoping to achieve at some point, is to provide this even as an online toolkit. And I'm trying here to refer to NOAA's Opus system, which is also very useful. So we're trying to see if we can mock that service and see if we can provide it as an additional thing online that people could use to process the data. I think with that, I conclude. I think I'm a little bit short. I mean, I finished earlier, so I think that should give us enough time for questions and answers. And if you'd like to reach out or contact me, again, my name is on the screen. And I think that's it. I'll get back to you, Tiffany.
Thank you, Samer. This is Katie, and I'm going to be reading through those questions that came in during the webinar. Okay, we had one come in fairly early, and the first question is the algorithm patented?
No, we did not patent the algorithm. So for now, if you're talking about protection, the way we're treating it is as a trade secret. We have not filed a patent. I did consult an attorney, and my understanding is with software, in some cases, it might be a little bit tricky, especially in anyway, so it's a long story, and he recommended copywriting and patenting. Sorry, not patent, copywriting and trade secret. And this is what we're doing for now.
Thank you. Our next question. So if you have to wait for the core's station data, how is this different from PPK?
PPK or PPP?
What the text of the message shows is PPK, and I'm unsure if the person who asked.
Yeah, I'm not familiar what PPK stands for. So if whoever asked would like to either reach out through an email or if there's enough time by the end of this Q&A and they can follow up, yeah, I'd be happy to handle that.
We did get clarification. It's post-processed kinematics.
Oh, yes. Okay, that's a good point. That's a very good question. I mean, quite frankly, when this SBIR was offered, it's given that we have long experience in high precision navigation systems, one thing we thought is going to be an easy project. I mean, we've done this a lot. We've done this post-processing kinematic, and even we at the time I was still even at the time when I was still a PhD student or a postdoc at school, I did write some of these algorithms myself. So I thought it was going to be an easy project to take. However, once you go through the requirements, you'll find that conventional PPK doesn't work out. So I can tell you that AccuTrace could be considered a specific way of running a PPK, just because of there are a lot of, I mean, if you run a PPK with the data we're doing now, probably your accuracy would be 4 to 3 or 5 centimeters, depends. But again, because of the requirements, if you assume that this is absolutely static, like geodesy applications, no, you could reach millimeter level. I mean, you could even go way below centimeters. But again, the requirements were tightening us in this case. So we cannot run the filter infinitely because these platforms could move, and therefore we have also to detect motion. We needed to use free sources like core stations, which means the distances are pretty long. Error modeling became a pretty critical component so that we can bring those errors down to that level. So short answer is I'm not aware of any commercial PPK that could achieve the accuracy with the requirement that NOAA co-ops had for us.
Great, thank you. And thanks for bearing with me as we discovered what PPK stood for. Our next question, is your error reduction algorithm sensitive to the geographic distribution of cores around the surrogate? The example you gave showed the surrogate fully surrounded by cores. At tide stations, you will only have cores to one side of the station, 180 degrees not covered by cores. So is it sensitive to that?
Yes, the answer is yes, although we were surprised in some cases that it was not. An example would be the one I'm showing actually here. Yes, we have coverage, but it's only, I mean, an ideal coverage of stations would span 360 degrees all around the antennas. In some cases where it's like this, we expected to not have very good results, let's say, meaning that we might reach centimeter or we'll be at the edge of 1.5 centimeters. But this is one of the cases that we could achieve that. There are other cases that were pretty challenging, and I recall that close to the keys over there, because now you're limited. Like your range of stations is all going in one direction. And of course, knowing how GPS errors have spatial dependency, having all stations on one direction would impact the accuracy. But there is no specific, like there's no one thing fits all. And in some cases we were surprised things would work fine, and in other cases didn't. It might rely on a lot of parameters or situations, including what the error sources were and how the stations were distributed.
Okay, great, thank you. Our next question, could the system be used along fault lines to help in predicting earthquakes?
So it depends how it's going to be used. I'm not expert when it comes how those systems work. So I'm pretty intrigued by the question and whoever asked it, and I would really appreciate if we have a side discussion, because I don't know, as I said, I don't know. Like if you want to use this for real-time earthquake monitoring, like what, for example, JPL is doing, it might not work because you might need something that gives you the data much faster than core stations. But I think if I understand the question in this case, no, they're talking about predicting, and therefore they're talking about small motion on the earth crust or the plate, the kind of plates, to see if there are some indications. But again, it's the lack of my background and knowledge in that I don't know, maybe, and I'm really open to further discussion to know how it works.
Great, Samer. We did have a clarification for that question. The person was asking more about mapping continental shift.
That is something that can be done in this case. We haven't tested it, and that's why. I mean, I'm in the top of my head, I don't see anything to prevent it. But again, I'm open to side discussion about it with whoever asked the question.
Wonderful. Okay, we're going to move on to the next question. Can the AccuTrace, can it know when the core's coverage is not sufficient? Is there a rule of thumb for max density, distance, etc.?
Yes. So there's a lot that goes into the software of trying to find surrounding core stations. It looks for, of course, it prefers to find the closest ones first. There's again, based on our work, we also have some list of stations that we started, we started marking as being not very good. That's part of the monitoring that we're doing, and therefore tries to avoid those as well. It checks different combinations in some cases to see what optimal configuration is better. We try to do some analysis on the side. And I think that's one of the things that we were hoping to get extra funding for. And I think for now we don't, but it's yes. So there's a lot that goes into it. If we cannot find, like in some cases, stations were far away, we did put a limit. Can't remember what the limit was, probably 150 miles or something close to that number. We usually don't try to take stations further than that, or maybe 200 miles, just because we know at that point that lots of the assumptions we're putting into this theoretically break down, and we know the accuracy is not going to be good enough. So we did put some limitations on not searching more than that, and then stick with whatever we have at that point. Like if we only have 3 stations close by, we'll use 3. We didn't go about beyond 6 because part of phase 1 was to look at the sensitivity of the number of stations, and we didn't see huge benefit going beyond 6 stations for us.
Okay, following up on that, how many cores are needed for each AccuTrace solution?
Right now we're using 6. One of the things that co-ops asked us to do under this new contract is to put that as a user parameter, that they wanted to say only use 4 and only use these 4. So that's another option that we added. So you could either leave AccuTrace to pick the best 6 stations, or you could force it to use a specific number and a specific number of stations as well.
Great, thank you. Okay, next question is, you know which cores to ignore. Can that be a separate product?
Yes, and that's the part that I mentioned about further work that we hope to get funding for. So absolutely. One of the things that when I mentioned it at some point in the slides today, is working with core stations over these 2 or 3 years of the project, and even a little bit after that, we've learned a lot throughout this process from what capabilities we can get from these stations, and at the same time, what could go wrong in these stations as well. So these are two different things that we're hoping to look for in the future, or look at in the future. So definitely we can now tell what stations are not good. In some cases, we might know why. In some other cases, I just don't know. It could be that the hardware is not working properly. And I don't want to step on anybody's toes here. I know that course division itself, they have their own monitoring going on. But we did see cases where maybe it could be good enough for 5 or 10 centimeter accuracy systems, but not for the one we're using now. So definitely we could put a monitoring software or a monitoring component for the core stations. The second part, which is using the course data, is that having data in real time would tell us a lot more information than just positioning. It could tell us, in some cases, what failures exist in the GPS itself. An example is there are certain faults and fault modes that happen in GNSS, including satellite failures. And I don't mean here failure that the satellite just stops broadcasting. No, it broadcasts, but it broadcasts the wrong thing or the wrong ephemeris message. Or there could be a maneuver that was not announced, or a satellite maneuver that was announced, but for some reason the flag to say don't use this satellite was not set up properly. There's so many fault modes that could happen, and did happen. At least I'm aware of 3 GPS-related faults that happened over the past 10 years, and 1 GLONASS constellation-wide fault where the whole, one of the parameters called Earth orientation parameter was broadcast wrong, which made it look like the whole constellation is just shifting. In addition to that, now we're seeing more of jamming cases, GNSS spoofing, and so there's so many things that could happen. Having these antennas and GPS receivers already distributed in the US could provide a lot of information about not only the station itself, but the reliability of the data in that vicinity. So we could use this data for a lot more than just providing position at this point.
Great, thank you. We do have a few more questions. This one here is from a user that may be a bit confused about the value proposition of this product. Does it tell if the primary measurement station moves, or is it intended to be a standalone measurement? Also, is this just vertical, or is it also horizontal?
So I'll start with the last one. For now, it's only vertical. Although the software, in order to compute vertical, you compute all directions, but we only output the vertical because that was the requirement in the project. The first question is, for now, the goal is just to look at the stability or how much the platform has moved, not necessarily to provide an absolute position. It can provide that, but that has a different requirement than the sub-centimeter.
Great. In follow-up, the title of this talk included level positioning. How was the leveling done?
How was the leveling done? Trying to understand the question. So, yeah, no, I'm not understanding what the question is. So if there's a follow-up, I'll be able to.
No problem. We can hook you up after the seminar with that question.
Mm-hmm.
Okay, our next question. Do you anticipate more motion once the antennas are mounted on a platform in water?
I missed the first part of the question. Can you read it again?
Yep. Sorry. Do you anticipate more motion once the antennas are mounted on a platform in water?
That's another good question, because maybe that's a detail that I didn't mention. So at the beginning, we were looking at two different platforms here. So one would be a rigidly mounted platform on water, like the one I used in the picture, where those are fixed to the floor of the water surface, whether that is a lake, river, ocean, etc. So those we don't expect too much motion because of the water itself, other than the whether it's so there's tide or even the tides themselves. But the other part was we were hoping that we could reach to the dynamic platform like a buoy, where in some cases you might put some scientific devices also on buoys. And we found that those are a little bit more challenging. I mean, we cannot reach a sub-centimeter in those cases. Part of the report that we provide to NOAA shows the feasibility when we go to something as dynamic as buoys, where they just float on top of the water and they just move up and down. So we did provide kind of a feasibility on that one on a different report.
Great, thank you. Couple more questions. Did you see any problems with multipath with the antennas you used?
Yes. So although we in the tests and even core stations, they all use high quality GNSS antennas, and in some cases even core stations use the multipath. Now I just missed the word. Like the dome to reject ground multipath. We did see in many cases, which was one of the reasons for mentioning bad stations. We did see some cases where the software kept triggering alarms that the data from the station is not good. The data from the station is not good. And we did notice that it's kind of repeatable. And therefore, one thing we did is to go on the core stations, look at the pictures, and we did see some cases where the antenna wasn't mounted in the best place that could be when it comes to multipath, and therefore we did attribute that to multipath. So on similar cases, we either flag that station as being not good for us, maybe we shouldn't use it, or if we want to use it, we use it during certain periods of time when we know that the satellite geometry with respect to the reflective surface is not hurting us.
Awesome, thank you. Our next question, could the system be used for a campaign-style survey, i.e. periodic observations?
I don't see anything that prevents from it, because as long as it's not required real time, as I mentioned, so you could take the antenna, put it in a specific place, collect certain period of data, and then go back and process it later on when the course data is available. Yes.
Great. Our next question. During your movement test at co-ops, the graph shows movement over 24 hours. I am assuming the movement was actually more instantaneous than that. What accounts for this difference?
Thank you for the question. That's something also maybe I missed mentioning in two slides. One is that the requirement when we set up the requirement with NOAA, one of the requirements was that the motion doesn't need to be detected instantaneously. So we did have a leeway of knowing that the motion is there within hours, and the magnitude of the motion itself, like the how much precisely it moved at 24 hours. So those two parameters, we use them in our filters, and therefore that slow motion that you see as a response to a little bit more rapid motion in the antenna is attributed to kind of a smoothing of the filters themselves.
Great, thank you. I'm going to grab one last question here. Can the accuracy be improved further?
Can the accuracy,
be improved further?
Can the accuracy be improved further? It's a tough question. I don't know. I mean, as I mentioned, I will just say that again. When we started this, I thought this is something easy and feasible. working on it, especially on phase one, even without real data. We did start seeing so many difficulties and challenges going through it in phase two. I don't know, for now, I mean, sub-centimeter, given the requirements we have now, the sub-centimeter is very, very challenging. I hope we could go more. I mean, if we have more stations, if we have more reliable stations, yes, we will definitely get more accuracy. But with what we're having right now, I don't know. I think that's what I would say the answer. I'm not aware of how to even improve it more. We've put everything we have on our knowledge and expertise in this software for now. But we're open to any suggestions or improvements in the future.
Thank you. While we were talking, we had 2 more questions come in, so we have the time, and I'm going to ask those. What about power and communication requirements at remote stations?
For power, there were power requirements, and that's one of the reasons that pushed us to specific hardware, and therefore we did not have any problem with that. I don't remember the specifics. It's been a long time because at some point we also moved from the hardware to the software. So we were assuming that these platforms already have solar power, and they have batteries for in case there's an overcast or etc. So we were giving a certain or we assume that we have a certain power consumption budget that we could use, and I think we did meet that requirement. The other question it was power, and what's the other one?
Communication requirements.
Communication, that was not part of AccuTrace. Co-op said that all these networks already have the communication mean. The only limitation for us was the bandwidth, and even for the bandwidth, the co-ops already told us this is what we want you to send in these times. And sorry if I don't remember precisely, but as an example, I'll use it like, oh, we want one message include the vertical and other parameters every, for example, 1 hour. And I think that covers the bandwidth side. But we were not part of the communication side, other than providing an interface, a hardware interface that meets NOAA's requirements. And I think I recall they wanted out to be through RS-232.
Right, this might have answered that, but what receiver, card, or chip are you using?
We're using, at the time, we used Septentria receivers, again, because we were limited with cost. We were limited with cost and power consumption. Mentioning that doesn't mean that this is the only receiver that would work. Like internally in TruNav, we did try it with other GPS vendors as well, but it was just a matter of different combinations of what would work, the size, the power, all these things played into making a decision of which receiver to use. Of course, as long as it's high end. I mean, we did try other receivers without mentioning names or manufacturers, and somehow the quality of the data that was coming out is not something that we were happy with. But there are definitely others that are pretty good as well.
Great, thank you so much, Samer. That was the end of our questions. If anyone does have further questions, you can either put them in the question panel or you can email Samer. He's back on his last slide with his email there. But if there are no questions, I'm happy to close this webinar for today and thank everyone for coming. And I hope you all have a wonderful rest of your Wednesday.
All right, thank you very much. And thanks for all the audience and their questions. I mean, some of them give us some potential ideas in the future, and I hope I answered the question properly. And as Katie mentioned here, if you have further questions, that's my email. If you'd like to have a side discussion about any other ideas, we're open. You could also check our website. I mean, we do a lot of other projects related to GNSS and navigation in general.
Great, thank you, everyone.